Okay, so in this video, we are going to look at a second optimization problem. This one will be a little bit more involved, and the setup is what we see here, that we have in an auditorium a with a flat floor, and there's this large screen, and the goal is to determine the value for x, so that variable there, which is the distance that we're standing away from the wall, that will maximize the viewing angle, which is this right here. Oops, which is this right here. So we want to maximize that. So the challenge in a problem like this is what I mentioned was the challenge in all these optimization problems, which is actually coming up with the function. So we need a function for theta where it's a function of x. So in other words, we need some theta as a function of x. And then we want to take the derivative, set it equal to 0, and maximize that. So that's going to be the challenge here that we have to work through. Okay. And part of the reason this is a challenge is, although we do have a couple of right triangles here, so we have this one here, this large right triangle here, right? And then we have this smaller one here. The angle that we're interested in, theta, is not in really either one of those triangles. It's in a triangle that is not a right triangle. So that's going to make the situation a little bit more challenging. Okay, so in order to set this up, I'm going to start out by pointing out a couple of different triangles that we have. First off, we have the very large triangle, right triangle, that looks like this, where if we call this x, we know that this is 10 feet. And so therefore, by Pythagoras, we know that this is x squared plus 100. Additionally, we have the smaller right triangle, which looks like this, where this is x, this is 3, and so this would be the square root of x squared plus 9. Now, for the purpose of this problem, I'm going to call this angle alpha, okay? And you'll note at this point, and just so you notice, that this is right here, this is where alpha is, okay? It's that angle there. And it's the same in the large rectangle as it is in, so now I'm going to draw a third rectangle, and it's going to be the one that sits on top of this small one. So it's kind of like this one right here, right? It's that one right there. So if I draw that, it looks something like this. And this is my angle theta. This is my angle alpha. I know that this is 7. I know this is x squared plus 9. And I know this is x squared plus 100. Now, this is going to allow me to come up with a function. So I'm going to redraw that triangle here. So we have this triangle here, where this is alpha, this is theta, this is x squared plus 100, square root, sorry, and then this is square root of x squared plus 9, and this is 7. And now if you recall back to your trig days, we know that in a non-right triangle, we can say that sine of alpha over the side opposite, square root of x squared plus 9, would be equal to sine of theta over the side opposite it, which is 7. So now notice I have a function of theta but now it's going to be a function of both alpha and x. So I need to get rid of this alpha. Well, if I come back to this blue triangle here, I can see here that in this triangle here, that sine of alpha is equal to, so that would be the opposite over the hypotenuse, it'd be x over the square root of x squared plus 100. So I'm going to replace that here. And so what I get is that x over the square root of x squared plus 100 times the square root of x squared plus 9 would be equal to sine of theta over 7. All right, so at this point, again, I want to solve for theta. So I'm going to multiply over by 7. So that's the first thing. This is going to get multiplied here. And then I'm going to take the inverse sine in order to isolate theta. And when I do that, I'm going to get this, that theta equals arc sine of 7x over these two radicals, x squared plus 100 times x squared plus 9. And this, now I have theta as a function of x. So now my job is to take the derivative. Now, I'm going to be quite honest with you. This is a little bit more of a painful derivative than what we've been experiencing in most of our optimization problems. Because when we take the derivative of this with respect to x, and again, we know that we want it with respect to x because the job was to maximize theta by determining the value of x. So how close should we stand? So that always tells you what you should have a function of and how you should take the derivative. Whatever it is you're wanting to maximize, that's your output. And whatever variable you're trying to find, that's your input. Okay, so we have to take this derivative. Now, it turns out that this derivative is quite painful. Notice you have to take the derivative. You're going to use the chain rule and product rule. But you have to take the derivative of arc sine, which is going to be 1 over. So what we're going to wind up with is 1 over the square root of 1 minus this whole thing squared. So notice what you're going to get. You're going to get a 49x squared over this times this, which is going to be x squared plus 100 times x squared plus 49. All times, now I've got to take the derivative of this, what's inside there. And that's going to be a bit of a pain in the neck. Because you could write this, we could put both of these up top and write them as, you know, to the negative 1/2 and do it that way, but then we still have to do a product, and it gets quite nasty. Okay, so I'm going to leave that to you. I'm going to show you what the derivative should be precisely. Okay, so the derivative should be, so if I have d theta dt, it winds up being this, negative 7x to the fourth minus 6,300 all over, let me do this, let me rotate this page here. I'm going to start over on that. I apologize, guys. But I think it'll be easier to see. Okay, so d theta dt is going to equal to negative, and then we're going to have 7x to the fourth minus 6,300 over, and then what we have on the bottom here is this x squared plus 9 raised to the 3/2 times x squared plus 100 raised to the 3/2 times the square root of the 1 minus that 49x squared over x squared plus 9 times x squared plus 100. Now, this, I want you to see that all this makes sense, because since this was raised to the 1/2, obviously now it would be raised to the 3/2 because it's negative So it became more negative, okay? But the key here is it actually turns out to be easy to solve for because we want to know when is this equal to 0, right? So that's the question. When is this equal to 0? Well, since this is a fraction, all we need to do is set the numerator equal to 0, and we get 6,300 minus 7x to the fourth, again, because of that negative, equal to 0. So 7x to the fourth equals 6,300. So x to the fourth equals 900. Now, if I take the square root of both sides, I get the square root of 900. Oops, I'm not sure what happened there. Square root of 900 equals the square root of x to the fourth. So then I get 30 equals x squared, which means that x is going to equal plus or minus the square root of 30. Now, we don't want the negative one because we don't want a negative value for x. So we're going to say that the answer is the square root of 30, which is approximately 5.477 feet. And that's the value of x that will maximize the viewing angle. Notice that if you're farther away from that, then because of the angle, theta is going to get smaller, right? And then as you get closer and closer, theta also gets smaller because of the difference between these two heights here. All right.